Alright, so for this next chapter, we're going to focus on 7 very important gas laws, or 8 in case I'm forgetting one. But first, let's revisit on some properties of gas particles and kinetic energy of gas particles and how that connects to Kelvin temperature. Alright, now with all this social distancing, let's say you wanted to go to the store and you wanted to take the family hot air balloon. Well, as you sit in the little basket under the balloon and wait for your servants to make your hot air balloon go up, I wonder if you should probably take some time and just think about it. How does your hot air balloon actually work? How does this golden hot air balloon work? That's what we're going to discuss right now. So, inside of your hot air balloon, right, are a bunch of particles, a bunch of gas particles inside, and they are moving extremely fast. They have to be in order to keep your hot air balloon expanded as much as it is. And just at the base of your hot air balloon, inside there is a flame. And if you want your hot air balloon to go higher, you have to increase the temperature, generally by increasing the flame. Well, when you increase the temperature, remember the particles are going to start traveling a lot faster. And as they travel a lot faster, their collisions within each other and along the walls are going to increase. And if you're increasing the amount of collisions, you're increasing the amount of force along the surface area inside the hot air balloon. And an increase in amount of force per unit surface area will result in an increase in pressure, which will sort of force the hot air balloon to expand a little bit more, and that's what allows your hot air balloon to go up. Every time you want it to go down, you'll decrease the flame, and as you decrease the flame, the particles will slow down. They won't be moving as fast. And because they're not moving as fast, they're generally going to be closer to each other as the volume starts decreasing, and its density also decreases. So as its density drops, the hot air balloon also drops as well. Alright, now forget the hot air balloon. Let's say you're going to take the family car out. Alright, so as you're driving down the street, paying attention to your driving, not being distracted by anything, you get a phone call or a text from your friend who says, hey, if you're driving, make sure you're driving safely and not looking at your phone. You look at it for a second, you look back up, you're not paying attention, and you hit something. And to keep it PG, let's just say you hit a stop sign, and something happens. These cars are designed where when there's an impact on some part of the vehicle, it sends an electrical signal, right, to your airbags. Your airbags, that electrical signal will start a reaction, and that reaction will generate a whole bunch of gas and inflate an airbag. And then that airbag will actually begin to deflate before you actually collide into it. And it's important that when you crash, you collide into a deflating airbag. You don't want to collide into an airbag that's inflating, because that's also going to hit you in the face as it's coming towards you. And so this happens in about, like tenths of a second. But it is that specific property of gases that we take advantage of. That specific property being compressibility. Compressibility is basically the amount of volume of matter that decreases under pressure. So obviously things that can decrease a greater amount of volume is more compressible than those that don't decrease in very much volume, which it turns out is because inside of your airbag are gas particles. And according to the kinetic molecular theory, here are a couple of assumptions that we have to remember. the gas particles, or the particles in a gas, are so small that the distances between them are so large that the volume, essentially, of each of these particles is negligible. It's basically nothing. And most of the space that's between gas particles is nothing. It's just void, empty space. And because you have that empty space, that's what allows particles to be compressed, because they're able to move closer to each other. The second thing to remember is that gas particles will travel in straight lines until they collide with another particle. And when they collide with another particle, they will change trajectory. And they're just going to be moving in straight paths until they collide, and then they change paths. And their speeds will change, but they don't travel in curved paths. The only way that they could travel in curved path would be a situation like this. If you had two particles that exhibited repulsive forces, as this particle is traveling this way and this particle is traveling this way, if they're going to repel each other, they're actually going to force their path to change or curve because they don't want to collide with each other. Ideally, this is not how we describe gases, and this is not part of the kinetic molecular theory. So for now, we're going to say that gases do not exhibit attractive or repulsive forces. Alright, so now we're going to talk about the four variables that are generally used to describe a gas and the common units that we use. The four common units are, we'll start with pressure. Pressure is often used in atmosphere or kilopascals. Those are the most common units that we'll use. The next variable that's used to describe a gas is volume, and typically your units are going to be liters. Another characteristic that describes gases is temperature, and this is extremely important. When we discuss temperature, when we do calculations that involve gases, temperature must always be in Kelvin. And the last thing that we use to characterize gases is represented by this symbol here, the letter N. The letter N means the amount of gases, or gas particles, or specifically moles. And so the next thing that we're going to discuss is actually how one of these variables can be affected by the other variables. We're going to look at how the amount of gas can affect pressure. We're going to look at how volume and volume change can affect pressure, and we're going to look at how temperature can affect pressure. And they're all interrelated, but that's kind of the perspective that we're going to use. Alright, so let's start off with how an amount of gas can affect pressure. Alright, so let's say that you were going to go out for, I don't know, let's say all this coronavirus stuff gets to your head, you can't really talk to people, and you just want to go for a nice bike ride. Okay, so let's consider two cases. Let's consider one case where you walk outside and you try to get your bike started and you realize that you have a flat in your front tire. Obviously, someone's getting fired. If we were to sort of zoom in side of the tire and kind of take a look at the molecules, it might look... Actually, let me redraw this. Okay, so let's say we're looking inside the tires. Usually, if you have a flat tire, you have less air in it. It doesn't have enough air, so you got to add air to it. Okay, so if we were to add air to the tire, then as we're adding more air to it, something starts to happen. As you're adding more air to the tire, you start increasing the amount of collisions all along the inside walls of your tire. And if you increase the number of collisions, you then increase the pressure, which in turn is going to make your tire sort of unflatten and sort of start increasing its volume a little bit, because you now have just so many more particles in there. So that's kind of a relationship of how pressure is affected by the number of particles. The more particles you have, the more collisions, and the more collisions you have, the greater the gas pressure. In fact, there's a relationship to it. As long as the temperature remains the same, if you double the amount of gas particles, you double the pressure. If you triple the gas particles, you triple the pressure. If you cut the gas particles in half, you cut the pressure in half. It's a very directly proportional relationship between the number of particles and the pressure, but only as long as the temperature remains the same. All right, now let's take a look at how volume can affect the pressure of a system. All right, now several gas engines use pistons and cylinders, so let's use that for an example here to kind of show how volume affects pressure. So let's say that we had a cylinder, and inside of the cylinder is a piston. And you might not know what a piston is, but it's basically this device that fits inside of some kind of chamber, and its function is basically to decrease the volume of things. So in car engines, pistons, which is this right here, pistons will move up and down to increase the volume and change the pressure inside of a cylinder, which is relevant to combustion engines. So that's not really what I want to get into here. So really what I want to show you is, let's assume that we're working with a very, very, very tiny cylinder that has 10 particles inside of it. And these are gas particles, so they're moving really fast. They're just moving around, bouncing around. So we know that there's a certain pressure inside of this container because it has gas particles in it. Now, what if we were to lower the piston? Let's say that this volume of space, which I know I said pretend we have a very small cylinder, but so that you can understand the concept, let's go back to just saying that the volume here is equal to 1 liter. Well, what if we were to push this piston downward? So I just went ahead and redrew it over here. So what if we push that piston downward and the amount of volume got cut in half? So now instead of 1 liter, your volume is now 0.5 liters. Now mind you, you still have those 10 particles. Okay, and they're still moving around, bouncing off each other and the walls. So my question for you would be, what do you think would happen to the pressure? Would there be a change to it? Well, hopefully your instinct tells you that, yes, there would be a change in the pressure, and that pressure would increase. We have the same number of particles, we've reduced the volume to half the original size, which means we basically doubled the number of collisions all along the inside walls. So there's actually an inverse proportional relationship between pressure and volume. So if the volume goes down, in this case it went down by a factor of 2, then the pressure is going to go up by a factor of 2. And that's how volume is related to pressure. That's so a change in volume can affect a change in pressure. And now finally, let's look at the last one, the relationship between temperature and pressure. And we've actually kind of talked about this before. So let's say we have some kind of container, it's closed, and inside this container we have a bunch of different gas particles, and they're traveling pretty fast at some average kinetic energy. And I'm sure we've said this before in class. So if we were to heat up this system, what would happen? Well, with an increase in temperature, we know that these particles would start moving faster. There would be an increase in their kinetic energies. And if they're moving faster, that means that they are colliding with the inside walls of this container a lot more frequently. And an increase in collision results in an increase in pressure. So that's the relationship between temperature and pressure. An increase in temperature, increase in pressure. Decrease in temperature, decrease in pressure. There is a directly proportional relationship between Kelvin temperature, right, or kinetic energy, and the pressure of a system. And we're actually going to save gas laws for tomorrow.